Hey everyone, it's Casey, and last video we started to look at how to turn alcohols into alkyl halides. Now last video we looked specifically at tertiary alcohols. That's an alcohol where the OH group is attached to a carbon that's also attached to 3 other carbons. Now for this video we're going to look at a primary alcohol, which is when our OH group, right over here, is attached to a carbon, right over here, which is itself attached to only one other carbon. So one other carbon. That's what we call a primary alcohol. And we're going to be turning that into an alkyl halide. Now, we see a similar trend, right? The OH group is getting directly replaced by whichever halide we have. In this case, it is a hydrogen, a bromide, with, they're just going to be switching. We see that it switches right over here. The OH is replaced with the Br, and we have a byproduct of water, something else that's going to be forming along with our reaction. That's the same. Now, why do we need another video for it? Well, the process to get there, unfortunately, is different. This is where organic chemistry starts to get a little difficult. So I'm going to try to expand on some of the reasons why we have little differences. So if you want to go watch the previous video to see, how did they do it with the tertiary, now we'll look at how to do it with the primaries. So you'll be happy to know that our first step is exactly the same. So for our mechanism, we're going to want to draw out what we have. So here's our primary alcohol, and I'm going to be drawing it in a structure format. I won't do bond line right away until you guys become a bit more familiar with how mechanisms work. So I want you guys to see each step because there's a lot of similarities, and in this one we'll have the same starting step. And what we do last time, we did a protonation, which is when we see our alcohol over here and we want to rip it up. We want to make room for our bromide or whatever halide we're using. We want to make room, but that OH is in the way and we want to get him out of there. We can't just go and rip this up right here. We need to find a way to rip that up. We're not capable of shrinking down and just destroying the bond or like breaking it with our hands. No, we can't do that. We need a way to trick the OH to get out of the way. And how do we trick him? We want to put a positive charge in him, because if he has a positive charge, he's going to be angry and he's going to rip himself off and he's going to leave. So that's the way we want to approach such a situation. And it will get its H or hydrogen over here from your hydrogen halide. Now hydrogen halides, you'll refer to them as acids normally in general chemistry and solution chemistry, like hydrofluoric acid, hydrochloric acid, hydrobromic acid, and sometimes hydroiodic acid. Those are all the same thing. I would refer to it as an acid. Like, if I wanted to dispose of a body, I would say I need an acid, and I would think of one of those guys. I don't want to say an acid though, because acid refers to a lot of things, and I don't want you guys to think that any acid would behave like this, but it's only these 4 particular acids that are part of like the 7th group of the periodic table. But anyways, we're going to have that same first step, and we're going to use our electrons from our OH, and we're going to attack that hydrogen, and obviously we'll need to get rid of the electrons that are in the bond, and we're going to put them on your bromide right over there. This step is going to be the same for pretty much every mechanism you'll see. There'll be some differences, but this one is very, very common. And we're going to have our hydrogen going on to your OH, and we'll have our bromide, that's going to be floating on its own, and we're going to have our 2 pair electrons right there and a positive charge. And like always, you need to make sure the charges from the reaction side add up to the charges from the product side. We have no charges whatsoever here, and we have a positive charge right here and a negative charge right here. Both sides add up to 0. It doesn't always have to add up to 0. It can add up to +1 as long as both sides are exactly the same. Now, we see right over here that we have a positive charge on this oxygen. Oxygen, very electronegative. It likes electrons. It doesn't like to have a positive charge. It's going to be angry, right? It wants to get as much electrons as possible. So it's going to be a bad neighbor, and it's going to start to, rip itself apart. Unfortunately, like we saw in the previous video with the tertiary ones, it can't just leave on its own. Since it is primary, it will not be allowed to simply, do like we saw last video where the bond just breaks and it forms, on its own. It will do this. Positive charge plus oxygen, or sorry, water on its own. This does not work. Let's actually go and get red right here, so I can just cross this out. No and no. This will not happen. The reason because of this, so let's go back to the green because the red's a little negative. We see this will not happen because it's not stable enough to pull something like this off. The positive charge on your primary little carbon structure over here is not enough. You need all of those surrounding CH3 groups to stabilize the positive charge. It won't be able to exist on its own. That's why, like we saw last video, this tertiary alcohol, which turned into a tertiary carbocation, was able to survive because you have all these guys contributing density of electrons to that positive right over there. They're not going to be doing anything. They're not actually going to be giving their electrons, but they're going to help stabilize the structure. We can't do this with a primary over here. We can't have a primary carbocation. It's not something that exists. So we need to find another way to get there. What's another pathway that we can use to pull off such similar results? Because we see over here from our overall, we will pull off the same sort of result. We will end up having the OH replaced with a halide. So how do we do it? We're going to pull everything off in one magical step. It's going to be very cool. So we're going to start off by going back to drawing what we had before. We're going to draw the exact two same things that we had from the products from our previous step because they're both going to work at the exact same time to pull off something pretty neat. Let's draw this one over a little bit more so we save some space. The stuff is about to get absolutely insane. So we see we have our positive charge and our negative charge over here. We're going to do one big switch at the same time because what are our requirements? We need to replace the bromine with the now little water leaving group that we have over here. We see that this forms water, right? And water likes to be on its own, so we'd imagine that this would want to get out of the area. We want to do the switch now. How do we do that without making a carbocation? We're going to have to do the switch at the exact same time. This guy is going to go onto the oxygen. So the electrons from the bond are going to go onto the oxygen, and it's eventually going to leave as water. We know that that's its main goal in this. And at the same time, the bromide is going to come in and attack the carbon that was attached to the OH. So I'm going to write that out because it might get a little confusing which carbon you want to attack. This guy over here is the carbon attached to your OH. It's going to attack right to there. Remember, we draw from the electrons in all cases. In this case, the electrons are in the bond and it's going to attack the oxygen. In this case, the electrons are in the bromide and it's going to attach the carbon. And how is that going to look in the end? Well, good news, bears. It's going to look exactly like we wanted it to. Yeah, I'll draw the hydrogen, water. Wow, that was a little bit of a fail right there. We have our water. And we have our primary alkyl halide that we so wanted to form. Right there. The fact that I'm writing in caps is not helping the situation in terms of running out of space. So we saw our whole process. We always start off with this first similar step where we're going to add a proton to the OH because we want to get rid of it. You always want to get rid of the OH. You know, it's taking up room. You want to take that space. The best way to do it in a primary sense is to get rid of it all in one step over here. And that's why we'd call it a bimolecular rate determining step because this is going to be your slowest step. Slow. You have a lot of things going on right there. And we're going to call this bimolecular. So let's look at that one last thing before we end off the video. A bimolecular. Because this is terminology that might be used on your test to answer like multiple choice questions. So I want to just make sure we don't overlook this. I think it's like an extra detail that should be learned a bit later on because it might make things a little bit more confusing. Determining step. Did I spell that right? Let's sure hope so. Okay, now what can we see in this? Rate determining step. This is going to be the slowest step in the sequence of all of these steps that we have. We saw that our mechanism could have 1 step, 2 steps, 3 steps. This is going to be the slowest one. And you know, you're always as weak as your weakest link. I think you're only as tough as your weakest link or whatever that saying is. You're only as fast as your rate determining step. You know, it doesn't matter how fast the other steps go. This one is going to be the slowest step. And if you want to increase the rate of your reaction, you're going to have to look at this step and see what can I improve in that step. So slowest step. Now, what do we see over here? We see the word molecular, and what does that make us think of? Molecules, not very useful. And then we see the word bi, and bi signifies two. Molecular signifies molecules, so essentially we have two molecules. Do we have two molecules interacting in our slowest step? Yes, we did. 1, 2. And those were interacting in the rate determining step, the slow step like we saw right over there. And then we saw in the other reaction, the one with the tertiary, we actually had a unimolecular rate determining step. You can see that a unimolecular, let's draw out like this. We saw in this case where we had, it was like this with our positive charge. It was capable because it was stable enough to actually just get rid of the group on its own. What am I doing? What am I doing? Right there. That's what I wanted. And we see that in this case, we only have one. This would be uni. Anyway, that's something I probably should have included in the last video. But anyways, remember, like we said, carbocations are reserved for tertiary only. Not something we should concern ourselves with primary. So anyways, I just want to throw in that last little note. You know, it's not necessarily important right now, but teachers seem to think it's important. It is important. I'm not going to say it's not important and your teacher is mean for teaching it. I'm just saying, you know, when you get all these fancy names in there, sometimes it's good to just learn the chemistry and not the naming behind certain parts of it. So anyways, that's the video. If you have any questions or comments, feel free to contact me on Twitter or in the comment section below. I think Twitter is the best way you guys can get in contact with me, and I'll answer you guys as soon as possible. So I hope you enjoyed this video, and I look forward to making some more of them for you guys. So have a good day.